A single vaccine that protects you against everything. Probably not well, but that doesn't mean it's impossible. This round structure is only about 10 billionths of a meter in diameter, but it, as well as other technologies in the pipeline, could be stepping stones to a monumental public health ambition. A single vaccine that protects you against everything. We'll get back to the grand vision later, but first, let's start with something that's being developed now. A vaccine that would protect you against every strain of the flu, even ones that don't exist yet. Here's one flu virus particle. On the inside is the virus's RNA, and on the outside are lots and lots of hemagglutinin proteins. Hemagglutinin attaches to a receptor on a human cell and fuses the viral and human membranes, starting the infection. Hemagglutinin is also one of the things your immune system recognizes and reacts to the most. To understand how this works, think of hemagglutinin as a bust of 19th century French Emperor Napoleon Bonaparte. Croissant. If you show Napoleon to an immune system and say, remember him, the immune system will mostly focus on his head. And the same is true for the real hemagglutinin. And one way the immune system remembers things is by physically interacting with them. Think of it as making plaster molds of parts of the head. We call these molds antibodies. The antibodies float around your bloodstream for a while and then can diminish, but blueprints on how to make them are stored in specialized memory cells, waiting for future Napoleons to invade. Here's the thing, though. Hemagglutinin is constantly mutating. Most mutations are subtle, produced by single-letter changes in the virus's RNA, like this or this. Over time, Napoleon/hemagglutinins head can change enough that our antibodies become less good at recognizing it. This is called antigenic drift. Influenza is constantly drifting. That's one reason you have to get a new flu shot every year. But sometimes bigger changes happen. An animal, usually a pig, can get infected with, say, a human flu and a bird flu. And those different viruses might infect the same cell. If that happens, the two different viral genomes can recombine in tens or even hundreds of ways. The human flu virus could pick up a bird flu hemagglutinin that's never infected humans before. This is called antigenic shift. And if you get infected by this version of influenza, none of the antibodies against Napoleon's head are going to help you. Antigenically shifted viruses have the potential to infect many people very quickly, causing epidemics and sometimes pandemics. A truly universal flu vaccine would be able to protect against current flu strains and future drifted or shifted strains. But how do we design a vaccine against a strain that doesn't exist yet? We look to the past. There are key parts of hemagglutinin that haven't changed much over time and are probably critical to infect human cells. These conserved regions could be promising targets for universal vaccines. But there's a problem that's hindered classical vaccine production. Many conserved regions are in the neck, and it's tough to get the immune system to react to the neck. Also, because influenza-like viruses have been around for hundreds of millions of years, there may not be a single region that's common across all species and subtypes of influenza. But there's promising science in development. Remember this? This is a protein called ferritin. Its normal purpose is to store and move iron, but it's also the rough size and shape of a small virus. And if you attach viral proteins to it, like this, you'd have something that looks to an immune system, like a virus, but would be completely harmless and very engineerable. Recently, scientists engineered a ferritin nanoparticle to present 8 identical copies of the neck region of an H1 flu virus. They vaccinated mice with the nanoparticle, then injected them with a lethal dose of a completely different subtype, H5N1. All the vaccinated mice lived, all the unvaccinated ones died. Going one step beyond that, there may be conserved regions that we could take advantage of across different but related virus species, like SARS-CoV-2, MERS, and a few coronaviruses which cause some common colds. Over the past few decades, a different part of the immune system has come into clearer focus. Instead of antibodies, this part of the immune system uses a vast array of T cells that kill, for example, cells that have been infected by a virus. Vaccines that train this part of the immune system, in addition to the antibody response, could provide broader protection. A universal flu vaccine would be a monumental achievement in public health. A fully universal vaccine against all infectious disease is, for the moment, squarely in the realm of science fiction. Partially because we have no idea how our immune system would react if we tried to train it against hundreds of different diseases at the same time. Probably not well. But that doesn't mean it's impossible. Look at where medicine is today compared to where it was 2 centuries ago. Who knows what it'll look like in another 50 or 100 years? Maybe some future groundbreaking technology will bring truly universal vaccines within our grasp.